Good day, everybody, and welcome to this third video on applications. Today, we're going to talk about the concept of rate of change. What is a rate of change? Well, there are two types of rates of change. Two types of how things are changing and the rate at how they change. And what are these two types? We have something that is called an average rate of change, and that simply corresponds to, well, how on average things change. It's about a line, it's about the slope of a line. So the rate of change, we're going to be considering this as a slope of a line, and the formula for the slope, as you know, is delta y over delta x. Yep. And the other type of rate of change, this one is instantaneous. Instantaneous rate of change. And that actually calls upon a much more recent concept that we have studied together. This will involve the derivative. Okay, so the derivative, of course, is, what is the derivative? The derivative is y prime, or what we have called dy dx in the Leibniz notation. So we're going to look at this, which is really an old thing, which is a slope between 2 points. And we're going to look at something quite different, which is the change at exactly 1 point. So this has to do with, of course, the tangent line and all that discussion we had before. Okay, so I want to illustrate all this through an example. And for that, I have selected something that some of us like to do, which is to play the stock market. Suppose a stock from the New York Stock Exchange can be, I'm going to use a word here, modelized. So modelized means I have a mathematical function that actually tells me how the stock grows and decays over time. By the function, P is equal to 3 ln x plus 1 plus 2 root x plus 1, where P is the price in dollars and x is going to be time. And here, just because it's convenient, I'm going to calculate time in terms of months. Okay, so for example, x equals 1 means like I bought the stock 1 month later, what is its value, right? And that value would be given by P, where P is obtained from this function. So the best thing to do here to sketch the graph of this is to give ourselves a few points. So x, P. The easiest point, well, also the crucial point, is at time 0. So when I buy the stock, I haven't held it for any time. So I'm buying it now. If you replace P by 0 to here, you're going to find $2. This is how I paid for that stock. Now, if I actually say, for example, I chose the x values that I chose are simply because they go well into the square root function. So if I choose x is equal to 3, I'm actually going to find that after 3 months, my stock is worth $8.16. So that stock is doing very well for me. So that would be 3. Now let's go to 8, because 8 plus 1 is 9. And the root of 9 is a nice number. So after 8 months, my stock is now worth $12.59. And after 14, no, not 14, 15, because 15 plus 1 is 16. After 15 months, my stock is worth $16.32. And after 24 months, which is a full 2 years, my stock is worth $19.66. Now, let's see if we can actually sketch the graph of this using the points that we are given here. Let us put this in a different color. Let us have here a y-axis and an x-axis. So x is time in months, while the y-axis is P, I'll put it on the other side, P in terms of dollars. P in terms of dollars. Okay, so x is equal to 0 gives me a 2 here. We're going to get something that looks like this. Roughly like that. Let me scale my x-axis. So this would be the largest point, 24. This would be 0. So halfway I would have about 12 here. So here's what? 6, 3, 9. And this would be 18 in the middle. And this would be 15 and 21. So let's put in some points on the graph. So 0, 2 like we put here, 3, and this point, that would be at a value of 8. So this is 2, that's 8, 16. We have 8 here, ballpark, which will correspond to 1259. We have 15 over here, which will correspond ballpark 1632. And we will have here 24, which will correspond 1966. All right. So the question here is actually to be using this curve to be calculating some average rate of change. So question, what are the average rates of change over the given period? So I'm going to give you different periods of time. For example, here between x is equal to 3 and x is equal to 24. So what I'm trying to figure out here is between 3 and 24, I have a straight line. Call it the first one. Call it the first straight line. And I want to know what is the slope of that line, because I want to know what is the change in price divided by the change in time. So delta P over delta X. So I take the price here minus the price there. So I take 1966 minus, what's the price at 3? 816. And I divide this by the number of months that the investment has gone through, 24 minus 3. And I get something that would be about 0.55. What are these? These are, what's a unit? It's very important. Dollars per month. So what does that mean? It means that over this long period, between 3 months and 24 months, 2 years, my stock has changed in value by plus 55 cents per month. It's not bad. Let's calculate the same thing between x is equal to 3 and x is equal to, say, 15. Once again, a delta P over delta X. This time it's the value of the stock at 15. So 1632 minus the value of the stock at 3, that hasn't changed. but the time interval has changed. It is now between 15 months and 3 months. So this here calculates the change in my stock over a period of 12 months or 1 year. Okay, so you calculate that and you get something like 68 cents per month. So this means what? That on average, my stock is changing in value of plus 68 cents per month. It tells you how my stock is increasing little by little. Let's do 3 to 8. X equals 3 and X equals 8. So once again, delta P over delta X. This time it's a change of value after 8 months minus the change in value after 3 months. So what do we got? 1259 minus 816. This time the bottom is 8 minus 3. Now we calculate that and we get something like 89 cents per month. So over this shorter period, at kind of at the beginning of me holding the stock, so after 3 months and then after 8 months, so this is over a period of 5 months, my stock was going up in a value of 89 cents a month. So let's put that on actually the graph. So the second curve, the second one is between 3 and 15. So 3 and 15 would actually be here. So you have the green line 1, the black line 2 here. You can see that there is a difference in steepness. Now the black one is steeper than the first one because the average value of the slope here is actually higher. And finally, I'm going to try this red thing, which hasn't been working for me of late, between 3 and this guy. You can hardly see it. That is the third one right here. Okay, they're a little bit sort of cramped together, but that's the nature of the beast. So you have a slope here in green, then a slope in black, and a slope in red, and the slope in red is the steepest of all. Now here's what I would like to do. You can see me coming with this. Now the question that I would like to ask is, what is the instantaneous? What is the instantaneous? Okay, rate of change, rate of change at precisely and exactly X is equal to 3. So after 3 months, I'm asking myself, not over a certain period, but exactly after 3 months, how fast is my value of the stock rising? So instantaneous rate of change means that I'm not taking an average between 2 points. I'm actually taking a value on the graph at that point. So the rate of change at a given point is going to be this. Is going to be the value of that line. So you can tell that basically the secant line, the secant line, the secant line, and at that point the interval between, well, 3 and 24, 3 and 15, 3 and 8, 3 and 3.1, 3 and 3.01, 3 and 3.0001. Finally, at that point, I get a line that should be a straight line that looks like this, and that is a tangent line. So the instantaneous rate of change is actually P prime, the derivative of that function, at X is equal to 3. Let's calculate P prime. We have it here. P prime is the derivative of this. So the derivative of this, perhaps we have room to do it here. It's not very complicated. So this is 3 multiplied by 1 over ln of x plus, 1 over x plus 1 times x plus 1 prime, which is 1, plus 2 times, root. We've done so many roots before. 1 over 2 root of x plus 1, right? So times x plus 1 prime. So this is my P prime of x. So when x is equal to 3, I get, well, I'm going to replace 3 into there. I'm going to get p prime, which is the slope of the tangent line to the graph of p at the value 3. So it's the rate at which my stock is changing exactly after 3 months. And that value can be calculated to be what? 3 plus 1 is 4, so 3 over 4. And 3 here, 3 plus 1 is 4. Root of 4 is 2 times 2. Oh, but it cancels out, so plus a half. So this is $1.25 per month. So that means that I buy it here at time 0 and it's worth $2. After 3 months, how fast is my stock rising? It's rising at a rate of $1.25 a month. That type of indication can actually help me decide if I want to hold on to the stock or if it's time to sell it. It is rising at a very, very fast pace. So in this case, that might indicate that it's time to actually hold on to the stock because it's still rising at a very good thing. On the other hand, if you take a look at after 2 years, it is growing at a rate of only about half $1 a month compared to $1.25 after 3 months. Well, it's not rising as fast. It's not gaining in value as fast. That could be an indication that it's time to sell. It depends on your perspective as an investor. So that's a good example using a stock value of how we can modelize this instantaneous versus average rate of change. I do have another example taken from, I guess, another little bit of a different perspective, not stock value, that I would like to present to you. So another example can be taken from population growth. Population growth. Let me explain what population growth here. I actually looked up a few figures on the internet, and I had to pick up a country that has a rate of growth in population that was interesting. Many countries are growing at a very, very slow rate. This country has a rate of growth which is actually significant. That's the word I'm looking for. So assume that the population of a country, assume that the population of a certain country changes with respect to time, changes with respect to time according to the following function. According to the function, and I'm going to give you the function here. So P of t is equal to 220 e to the 0.021 t. So that's a function with an exponential, with an e, with an exponent and a constant in front. Okay, so let's dissect this a little bit and see what it actually means for us. Change a 220 to a 221. Here, my mistake, 221. So when t is 0, let's make a little graph of this. When t is 0, we have something interesting about this. So when t is 0, we have that e to the 0, well, times this is 0, so that's 221. That's my initial population at time 0. Time 0 can be anything you want. Now, the numbers in here are actually taken from the year 2020. That's why I put a 20 here instead of a 21. I had 20 in mind. So these are recent numbers. This is like COVID year 2020. So basically, it means that right now the population of this country is 221, and it's not 221 inhabitants, of course. The population is going to be given to us in terms of millions of people. So it's 221 million. So couple more points. So in 5 years and in 10 years, let us see what this model tells us what the population of this country will be in 5 years. So we need to put 5 into here, and if we do so, we are going to get 245.5. Remember, these are millions. And if I put 10 into here, so that becomes like really, really big, then I get something like 232.6 million. These are all in millions of dollars. And if I make a sketch of this, changing colors, if I make a sketch of this, you remember the graph of the exponential function, guys? What it looks like, right? So this is going to be t time in years, and this is going to be p population in millions, right? So remember the graph of an exponential? The graph of an exponential is something that starts with like very far this way, goes up, goes up, goes up, goes up like this, and the x-axis is a horizontal asymptote because the limit as t goes to negative infinity is 0. So it's going to give us something like this, like that, right? Now, the thing is, we don't really consider any negative years, so we can get rid of this part over here because it is not part of the graph. T is a positive value. T goes up in years, so here's 0, and here's 5, and here's 10. So we have a few points on this graph. We have here 0 and 221. At 5, we have 245.5. And at 10, I'm going to have to erase my millions here to fit this into this extremely small and confined space. This actually is this guy, 232.6. Again, the question will be, what is the rate of change? How fast is the population growing in that case, right, of this country? So what is, back to blue, so what is the average rate of change for the given intervals, for the given time intervals? So let us take a look at, say, 0 and 10. So t equals 0 and t equals 10. So basically, again, what I'm doing here is I am taking a line, let's call it line number 1. I'm taking a line, I'm connecting 0 and 10, and I want to figure out what is the slope of that line. So the answer is delta P over delta T, the change in population divided by the change in time. The population after 10 years was 232.6 minus the population at time 0 was 221, and I'm asking for this change of population. So you see, the population of that country has been changing by what? 11.6 million people over the span of 10 years. So to calculate, that is easy. We get, what do we get? We get 5.16, I think. 5.16 million people per year. This is an average. So what is this? This is the answer to what question? This is the answer to how fast is the population changing between 0 and 10 years of this country? Well, the population of this country increases by a factor of 5.60 million per year on average. This is an average rate of change. So now let's do the same thing between 0 and 5. So between t is equal to 0 and t is equal to 5. The delta p over the delta t, the change in population divided by the change in time. T is equal to 5 is 245.5 minus, add times 0 to 21. So this time I got an increase of what? 24.4 million people, but it's over a span of 5 years. So if we do the math on this, we are going to get 4.89 million. 4.89 million people a year. This is your average change in the population, right? And this line will actually, we'll put the first one in green. That was number 1. Let's put the second one in black. That'll be number 2. So 0 and 5 would be here. As you can tell, the orientation of the lines on the black one is actually a little flatter. And now what I'm going to be asking is the instantaneous rate of change. So what is the instantaneous rate of change at time 0 when t is equal to 0. So not an interval anymore. Now a specific point on the graph. At time 0, which we can assume, for example, in this problem is the year 2020. What is the, how fast is the population changing today, now? That would actually correspond, well, I got to be careful here. I got to try to make something that looks like a tangent line to the graph. So this is, I should have put here number 2 for this one here, the black one. And this is number 3. This is the red one. This is the red line. And the instantaneous rate of change is p prime when t is equal to 0. So what's p prime? Let's derive the function that we have here. Let us derive 221 e to the 0.021 t. Well, the constant plays no role. The derivative of e to the u is e to the u, 0.021t, times u prime. What's the derivative of 0.021t? It's 0.021. 0.021, close bracket. So p prime of 0 is 221 e to the 0 times 0.021. And if you throw this into the calculator, you're going to find something that corresponds to 4.64 million people per year. And that's your instantaneous rate of change. This is how fast the population is growing in 2020. As you can see, it will grow at a faster rate later on because the curve is an exponential curve and its slope will get steeper and steeper as you actually get higher into the curve. So the bottom line here is to actually remember that the average rate of change is the slope of the line between 2 points, and the instantaneous rate of change is actually the derivative of the function taken at a specific point. More to do on this when we meet in class and on the lab and so on and so forth. I hope this was interesting to you, and I will see you next with the last application, which is also the last topic of the course. In the meantime, I wish you well. Take care.